99.9% of American households own and operate a refrigerator. So why does the majority of the population not understand how this vital component of modern civilization operates? In order to understand refrigeration, we must first explain some key laws, definitions, and phenomenon. The sensation of cold is in fact the absence of heat, so in order to produce cold, we must remove heat from the system. The first law of thermodynamics states that energy can neither be created nor destroyed. Thus, to produce cold, we must transfer heat out of the system and into the environment. The second law of thermodynamics states that two systems in contrast will tend towards an equilibrium. This means that a cool substance will draw heat from its surroundings, and similarly, a hot substance will dissipate its heat into its surroundings. Finally, when a substance is compressed, we must understand its volume decreases, but the amount of latent heat within the substance stays the same. This concentrates the heat energy and raises the temperature of the substance. These key concepts allow the refrigeration cycle to remove heat from the system and transfer it into the environment, cooling the inside of the system. The refrigeration cycle begins when refrigerant is compressed. As we said before, this reduces its volume, raising its temperature above that of its environment. Because the refrigerant is now hotter than its environment, it dissipates its heat into the environment to reach an equilibrium. When the refrigerant is then returned to its nominal pressure, there is an absence of heat from that heat ejected previously. The refrigerant then absorbs heat from its surroundings, producing cold. Now that we understand the basic cycle of refrigeration, let us take a look at how this cycle is achieved mechanically and the effects each stage have on the refrigerant. To begin the cycle, the evaporator valve opens and allows the low-pressure, cool, saturated vapor from the suction line to fill the chamber. Once the chamber is full, the condenser coil valve then opens and the piston compresses the refrigerant. Compression concentrates the heat in the refrigerant, changing it from a low-pressure saturated vapor to a high-pressure gas. The high-pressure, high-temperature gas must condense to allow its temperature to reach an equilibrium with its surrounding air. To aid this process, air is drawn in through these intake openings and pulled across the condenser coils by these two outtake fans, pushing out the warm air and replacing it with newer, cooler air. This dissipates the latent heat and condenses the refrigerant into a high-pressure but room-temperature liquid. The expansion valve then depressurizes the high-pressure liquid refrigerant, returning it to its nominal pressure. Because of the speed at which depressurization occurs, half of the refrigerant is instantly evaporated into a saturated vapor. This mixed vapor and liquid refrigerant is then run through the evaporator coils that are connected to the cooling tunnel by aluminum leads. These leads allow the refrigerant to draw heat from the air inside the cooling tunnel to replace the heat dissipated into the environment by the condenser coils. This fan circulates air from inside the system along the aluminum leads. As this air travels down the cooling tunnel, heat is removed from the air and transferred into the refrigerant. The air is then pushed back into the refrigerator to cool your food. As the refrigerant approaches equilibrium with the air inside the system, the remaining liquid refrigerant evaporates into a saturated vapor. Eventually, the refrigerant reaches a temperature above the desired temperature for the inside of the system. The compressor must then draw this refrigerant in again so the cycle can continue and your foods and goods are kept cold.